Now getting into the real substance and calculations that we're going to be doing in this chapter, we want to use these formulas that we're going to see about how to find the mean and standard deviation of, and this one, it's such a mouthful, sampling distribution of the sample mean, which here we just abbreviate sampling distribution of x bar because of course x bar is the sample mean. We will have a little definition here that if you're taking simple random samples of size n from a large population that have the mean mu and the standard deviation sigma, then the sampling distribution of the sample mean will have its mean, which we will write as mu sub x bar. That's going to be the mean of the sampling distribution of the mean. It will be the same as the population mean, so that's really fantastic. And then the standard deviation of the sampling distribution of the mean, we will write it as sigma sub x bar. That's going to be the standard deviation of the population and then divided by the square root of the sample size. So these are really nice formulas, really easy to use compared to obviously some of the formulas we've seen before. These look fantastic. But there's a couple of side notes here, which this one makes sense. If the original population is normally distributed, then the distribution of the sample mean will also be normally distributed. And here it doesn't even matter the size of the sample. But if the population is not normally distributed, and this is something that's so nice about this distribution of the sample mean, is that even if the population is not normally distributed, then the distribution of the sample mean will be pretty much normally distributed, especially as n increases. It will, as the sample size increases, it will become more and more normally distributed. And we will use still the same calculator buttons for this one because what we're dealing with, the distribution of the sample mean, since it is normal, as n increases, but n is pretty much, it's always going to be large enough. It's not a bother for us. We're going to be able to treat this now as a normal distribution, regardless of how the population is distributed. And so we'll be able to use still the normal CDF for our purposes. And why don't we see actually an example here. And that, by the way, this last note, it just gets its own special name, which is called the central limit theorem. But all that's saying is that as n increases, then the sample distribution of the sample mean will be more normal all the time. Now, we're dealing with an example of IQ scores. What else? This is such a useful example for us. It says the IQ score for adults is approximately normally distributed. We know this stuff. The mean is 100, standard deviation is 15. We've all seen this before. Now it says if one adult is chosen, find the probability that they have an IQ score greater than 100. So what we've already seen is that for this kind of a situation, we're just going to pick an adult, and this is basically what we've seen already in Chapter 7. This problem would be suited for Chapter 7. If you're just reading it, I know we've just gotten done talking all this stuff about Chapter 8, but if we just take a step back and we read this, we've got an adult. We're going to take a sample of one adult. We're trying to find the probability that they have an IQ score greater than 110. So we're thinking about, this is a distribution for IQ scores. The mean is just in the middle, it's 100. Standard deviation is 15. So this would be like 115 would be here. And it's hard to draw the 5. And then we've got 100 is the mean. What's the probability they have an IQ score greater than 110? So 110 maybe is kind of here. The probability that they have an IQ score greater than this is just the area, right, underneath this curve. And so we're going to use our handy dandy distors. We will go normal CDF. The lower bound in this case is 110. That is the value that we're looking for. The upper bound, it's just going off zooming to infinity, so we will use our pseudo infinity button. The mean is 100. the standard deviation is 15, and now we're going to get the area of that little tail up there. It's that much, so we will say the probability to pick an adult at random and have IQ score greater than 110, it goes 0.252, and then we should round up the 4 because it goes 49, so we will call it 2525. So now, what about if we have such a question as this? If 9 adults are chosen, find the probability that their mean IQ score is greater than 110. So what I'm drawing now is not the same picture as what we had before. This distribution, this is going to be the distribution of the sample mean. And we're taking samples of size 9. So we're imagining, if this is just in the United States or whatever, the population of adults is gigantic. It must be some kind of, 100 million or something. So you can imagine the number of samples of size 9 that you could take out of a population of 100 million people, for example, is, it will probably overflow the calculator if you try to calculate that one. But here what we're dealing with obviously is a sample. 9 adults, that's the sample, that's the little n, is 9 in this case. And we're trying to find the probability that their mean IQ score. So we're talking about the mean of a sample. So here, this is a distribution of the sample mean. And we're still using the same value. So here goes the middle. So 110 maybe is here. But the shape of this distribution, as you see in this picture down here, it's affected by the fact that n is 9, this pink one, or whatever color you're interpreting this to be, this would be the sampling distribution of the sample mean, and you notice how it has even a higher peak and it's even more narrow than just a regular normal distribution. And here we're looking to find the probability that their mean IQ score is greater than 110. But since this is the sampling distribution, the mean is going to be the same because we already saw before that the mu sub x bar is the same as mu. So they are both 100. And then the standard deviation though is going to be a little bit different. The sigma sub x bar, we saw that one is sigma divided by square root of n. And so the sigma for the population, the standard deviation for the population is 15. And then we're dividing that one by square root of little n, which little n is the sample size is 9. So we're dividing 15 divided by square root of 9 is 15 divided by 3. So that standard deviation is actually just going to be 5. And now we're still talking about this area. We want to find the population to land inside of this area, or the probability rather. And so we will still go to vars. Second vars gives us distor, normal CDF. In this case, the lower bound is still 110. The upper bound, it's still zooming off to infinity, but now, since the distribution that we're dealing with, it's normal because the sampling distribution of the sample mean is normal. That's the whole thing that we're talking about with the central limit theorem and so forth. We can still use normal CDF because it's a normal distribution. The mean is 100. The standard deviation is the one that we find this way, which we found is 5. And now, what is going to be the area this time? See, it's even much less likely. So the answer, is not a good place to put it, is I will just give it goes 0.022, and then we round always to 4 decimal places, remember, and so this should go 8. So if you take a sample now of 9 adults and you find the mean, it's even a lot less likely that the mean will be 110 than it is just for an individual person, which makes sense because you will get people with lower IQs that will lower the average and so forth. Now, we're going on to some more examples. What about for women aged 18 through 24? The systolic blood pressure are normally distributed with mean of 114.8 and standard deviation of 13.1. If you select a woman at random, this is what question A is talking about, find the probability that her systolic blood pressure is greater than 120. So we have kind of our normal distribution. It says that it's normally distributed. It has mean of 114.8, and it has standard deviation of 13.1. So this value of 120, it's just, maybe a little bit more than the mean, not a lot. We're wanting to find this area, because that will be for somebody who's greater than 120. That's what this data value here is intended to be, 120. Then we will just do it the familiar way. We should go normal CDF. And we're finding with the lower bound of 120, upper bound is just going towards infinity. The mean is 114.8, and the standard deviation, it tells us, is 13.1. So what is the probability for this woman? It's about a 1 out of 3 chance. It's really semi-likely. It depends what you're calling likely. It's definitely not unusual to have this happen. 0.3457 is what we get there. Now what about, though, for example, you select 36 women. You're taking a sample now, and then you find the mean of the sample. What's the probability that that's greater than 120? So the mean of the sample distribution of the mean, it's the same as the mean for the population. It will be still 114.8. And I know this is not looking too good. And then here, maybe we're calling this 120. And so we're talking about kind of this area, right, this tail. But we need to find, we found that the mu x bar is going to be 114.8 because it's always the same as the one for the population. But what about the sigma x bar? It should be the standard deviation for the population, which is 13.1, and then divided by the square root of the sample size, which is square root of 36. It's a very nice number for us because it's a perfect square. So we're looking at 13.1 and then just divided by 6. That will be the standard deviation for this one. And we can actually probably just go right into the normal CDF with those numbers. Lower bound is 120. It's all the same. And then in this case, we want actually, can I just do divided by 6? It works. So in this case, you take a sample of 36 women. Now it becomes actually very unusual that you will take a sample that has, I will go 8, 6. It is very unusual to get a sample that will have such a mean that's more than 120. And this will all go into what we're doing later, where we're testing hypotheses and so forth, because we want to say, look, this is our sample and the sample has such a mean. It would be extremely unlikely for the mean to be over this amount if, the mean of the population actually is something else. And so this is going to go towards our ability to make predictions and to just analyze data better.